So in the last video, we introduced the definition of Doppler effect. We also gave the definition of the Doppler equation, right? So we also did a scenario where it was my source of sound was approaching a certain listener, and where my source of sound was moving away from my source of where my source of sound was moving away from my listener, right? So, but then before we continue with today's video, I also wanna show you a scenario where my source of sound is stationary. So if, let's say, this is my source of sound, right? So if my source of sound is stationary, these are concentric circles. So what I mean by concentric circles is that the distance is equal, right? And then let's just use the same people. So this is Mike, right? And this is Tim. Tim is Mike, right? So in this case, my wavelength is equal. So this is my wavelength, right? This is my wavelength, this is my wavelength, right? So because if I find that my wavelength on Tim's side, like the wavelength on Tim's side, which is this, is equal to the wavelength on Mike's side, right? It means that the source of sound is stationary, because if the source of sound was moving towards either Tim or towards either Mike, right, they wouldn't have the same, the wavelength wouldn't be equal, right? But then to show that my source of sound is stationary, I'm going to have equal wavelength on both sides. And if my wavelength on both sides is equal, it therefore means that Mike and Tim will register the same frequency, right? So, but then because there is no relative motion in this case, right? No relative motion. So in this scenario, Doppler effect is not what? Doppler effect is not observed. Because remember, in the last video when we were starting, we said in order, the condition for Doppler effect was that there has to be relative motion between my objects, right? So if one is stationary, the other has to be moving, and vice versa. That's what has to happen in order for Doppler effect to be observed. But then in this case, Mike is stationary, Tim is stationary, and also my source of sound is stationary, meaning no Doppler effect is being what? Observed. I hope you understand that. So let's get started with today's video. So today's video, we are gonna be doing a scenario for approaches, as the source of sound approaches somebody, right? So let's start with for approaches. So this side, let's just do a table. This side I'm gonna have a stationary source, right? So I obviously know that when my source is stationary, it means that the velocity of the source is what? The velocity of the source is equal to 0, right? This is approaches. And if my listener, is stationary, right? So two things can happen here, right? With approaches. I, as the listener, can approach the source of sound, or the source of sound can approach me. So if me as the listener, I'm stationary, that means that the velocity of the listener is equal to 0, right? But then remember, we said if with approaches, as long as the source of sound is approaching me, or I am approaching the source of sound, I have to register a frequency higher than the source of sound, right? So with approaches, one thing you have to know is that the frequency of the listener will always be greater than the frequency of the what? of the source of sound, right? And because the frequency of the listener has to be greater than the frequency of the what? Of the source of sound, we therefore go to our Doppler equation, right? Meaning my Doppler equation is now going to be FL is equals to V plus VL. You see, it was a plus minus. The reason we chose a plus is because my numerator is increasing in size. Because for my FL to be greater than my FS, which is my source of sound, right? It has to have a larger numerator, right? It's just basic 1 over 5. As my numerator increases, right? My If you go 1 over 5, we basically know 1 over 5 is 0.2, right? And then if you increase your numerator 3 over 5, you're gonna get a much larger number than what? Than 0.2, which is gonna be 0.6. You see, so as my numerator increases, my what? My answer increases. So that's why we say plus, right, instead of minus. But then because as my numerator increases, I want my denominator to decrease so that my FL is greater than my FS. So it's going to be V minus VS, right? So from here, right, we already know that VL is equals to 0, right? So this is going to be FL is equals to V plus 0 over V minus VS, which is going to be FL is equals to V over V minus Vs, right? So we said V is the speed of sound in air, and you are mostly going to be given the speed of sound in air, or if you're not given, we are going to assume that it's 340 meters per second, right? So this is when my listener is stationary and my source of sound is approaching me, right? But then we also have a situation where my source of sound is stationary and the listener is approaching the source of sound, right? So if my source of sound is stationary, we obviously know that its velocity is going to be what? It's going to be 0, right? Meaning that my FL is equals to, because it is still a situation where we are approaching something, my numerator always has to increase while my denominator decreases, right? Just just sit down and try to make sense of whether you choose a plus or minus, why we choose a plus or minus with the approaching situation, and you kind of see why we do that, right? So this is going to be V plus VL over V minus VS, right? Because the source of sound is stationary, obviously, so this can just be written as V plus VL over V, because Vs is equals to 0, right? So this is a scenario when I am approaching the vehicle or the vehicle is approaching me. So with approaches, you just have to know that my frequency of the listener should always be greater than the frequency of the source. So an example of this, I can just say, let's say we have a car, right? And the frequency of the source, that car is emitting a frequency of 480 hertz, right? Right? And then we have a listener. Let's say the car is approaching me, right? So because the car is approaching me, we said with approaches, the frequency of the listener should always be greater than the frequency of the source, right? So when calculating, I cannot get an answer that is less than what? That is less than 40. I have to get an answer that is greater than 480, right? So an answer which is greater than 480, we can just say 490, right? We can just say 495. We can just say 485 hertz, right? So as long as my answer is greater than the what? Is greater than the frequency of the source, right? It's an indication that I have done my calculations correctly, right? Because I cannot say with an approaching situation and when calculating, I find that my frequency of the listener is less than the frequency of the source. That means I did not do something right when calculating, right? So this is my approaching situation, right? So for my moving away situation, it's gonna be like this. So this scenario is when either the source of sound is moving away from the listener, or the listener is moving away from the source of sound, right? So two things can happen. The source of sound can be stationary while the listener is moving away, meaning that the velocity, the speed of the source of sound, right, because it's stationary, is going to be zero, right? Or the listener can be stationary while the source of sound is moving away from the listener, meaning that the velocity of the listener is going to be zero, right? So with moving away, because now my car is moving away from me, it's going further and further and further away from me. Like, it's just like the example I gave in the previous video. I gave an example of a car that's playing music, right? So right now, imagine yourself standing next to a car which is playing music, right? So as the car is moving away, further and further away from you, what do you notice? You start to hear less of the sound, right? The sound starts to fade as the distance between you and the source of sound what increases. You understand that? Meaning that for moving away, my listener, the frequency of the listener has to be less than the frequency of the source of sound. I cannot register a frequency greater than the source of sound if the source of sound is moving away from me, or I am moving away from the source of sound, right? So I hope you can differentiate when the source of sound is approaching me or when I am approaching the source of sound. That means I'm going to register a higher frequency than the frequency of the source of sound. But then when the source of sound is moving away from me, I am going to register a lower frequency than the frequency of the source of sound, right? So because right now my the frequency of the listener is less than the frequency of the source of sound, right? So when we go to our Doppler equation, which is FL is equals to FL is equals to V, right, plus minus VL over V plus minus VS times Fs. Oh, and then in the previous video, I forgot to multiply this thing by Fs, right? So in the previous video, you just multiply by Fs. I forgot to do that. Okay. So here, right, we now have to determine whether it's a plus or a minus. But then because we are now moving away, that means because I am moving away, my denominator has to increase while my numerator decreases, right? And I just said for you to understand what's actually going on, you have to sit down and actually think, why do we increase the denominator and why do we increase the denominator and decrease the numerator as my source of sound is moving away, or I am moving away from the source of sound, right? So for this, it's just going to be FL is equals to V minus VL over V plus VS multiplied by Fs, right? So in the approaching scenario, right, it was V plus VL over V minus Vs because we are approaching and we want the frequency of the listener to be greater than the frequency of the source of sound. But then right now here, we want the frequency of the listener to be less than the frequency of the source of sound. So that's why we are subtracting on the numerator and adding on the denominator, right? So the same is just going to apply on this side. So this side is just going to be VL is equals to V minus VL over V plus Vs multiplied by Fs, right? So if we just fixed our mistake from the previous slide, right? So in this slide, right, we were supposed to multiply by Fs. I forgot that. So this is just multiplied by Fs, multiplied by Fs, and Fs we know it's the what? It's the frequency of the source multiplied by Fs multiplied by Fs, right? So that's the mistake that we wanted to fix. So that's the scenario for moving away and also approaching, right? So in the next video we'll be doing graphical representations. They're quite easy. It's just gonna be a 3-minute video, because there is one type of graph that you're gonna encounter in Doppler effect, right? And the graph that you're gonna encounter in Doppler effect, it's only going to be a scenario where it's only for one listener. In the grade 12 syllabus, we do not do the graph, the graphical representation for 2 or more listeners. We only do for one listener, right? So I hope you guys subscribe, like, and comment, and I'll see you on the next video.